Hello everyone and welcome you all for today's lecture. We will briefly look at what we did last time and then proceed further for the other aspects of asymmetric reactions. So last time what we discussed was Katsuki-Jacobson epoxidation and the mechanistic aspects of it towards the end, and followed by we did introduction of the dihydroxylation of olefins. So in the case of Katsuki epoxidation reactions, various aspects of it we saw how the different types of C2 symmetric based 1,2-diamines and different aldehydes, which are basically salicylaldehyde derivatives, are used to make the manganese oxo complex, and that allows epoxidation to take place based on various factors and then allows highly enantioselective epoxidation. In that respect, when we looked at the mechanism, if we start with a cis olefin, then we saw that there could be a possibility of a manganese complex which is basically having a 2+1 type of intermediate. That means it gives you a 2+1 concerted process to lead to this, which allows the epoxidation to complete by the release of manganese 3. So we start with manganese 5 and then we release the manganese 3 upon epoxidation. We also saw that since cis olefin gives cis epoxide, therefore this type of concerted process is important. We also saw that it can also be done by a metallo-oxetane type of intermediate where something of this kind can be proposed, and when this breaks up in this fashion, then we can also expect the cis epoxidation to take place, and plus of course manganese catalyst goes away. But this was also expected to form a sort of radical in some way or the other, so that we can expect that there is a possibility of a radical formation here, and of course a radical can come in here, and then there is a rotation, and then that can allow the epoxidation eventually to form in this way that some amount of trans epoxide is formed. So considering these aspects, there is a possibility of such a radical based reaction to occur, especially in cases where the cyclopropane ring becomes a part of the starting material. So these are the aspects that we saw, and then we also looked at the dihydroxylation of olefins using osmium tetroxide. But since osmium tetroxide is expensive and toxic, and therefore there is a need to use that in a catalytic amount, and towards the end we looked at the use of co-oxidants, and where we discussed sodium chlorate and also hydrogen peroxide, but then these lead to over-oxidation. So there was a problem, and therefore there is a need to look at the co-oxidants in a different way. So later on Sharpless also did some work in this area, and many other people, and accordingly Sharpless introduced the tertiary butyl hydroperoxide along with osmium tetroxide as a co-oxidant, and in the presence of these salts to kind of dissolve the reaction and the aqueous condition. And also N-methyl morpholine N-oxide NMO was used as a co-oxidant by Upjohn company, and that is why it is known as Upjohn dihydroxylation. because it was they who first developed the use of N-methyl morpholine N oxide in the dihydroxylation. So, this is the this NMO, that is N-methyl morpholine N oxide, which is what is something that we had discussed earlier. And one of the first attempts to make it chiral was then looked at it, because now since osmium tetroxide is not required in a stoichiometric fashion, and therefore one can now start looking at whether reaction can be made it as a catalytic and also asymmetric. Now we mentioned or we discussed earlier that there was a possibility of increasing the rate of reaction and increase the yield if a tertiary amine or a pyridine is added to the reaction mixture, and that allows the attachment of the the tertiary amine or the pyridine to the osmium atom, and therefore the reaction rate increases. Considering that the chiral ligand, which is pyridine based, was used for the first time, and it was found that eventually there was an optical kind of induction or asymmetric induction, and that gave the optically active molecules in 3 to 18% enantiomeric purity. However, this particular chiral ligand, which is this, where there are 3 asymmetric centers, and it was found that since pyridine moiety is very close to the isopropyl group, and therefore it is something could be sterically not desirable, and therefore the large group close to the nitrogen sort of prevents the pyridine to come very close to the osmium because of the steric hindrance. Later on many people like Narasaka, Sainder, Hirama and Kori studied different types of C2 symmetric based bidentate amine ligands which are shown here, and different types of these ligands gave very high enantioselectivity, more than 99% for trans-stilbene, but it was not catalytic in terms of osmium tetroxide or the ligand. That means even these chiral ligands which are shown, these structures of which are shown here are need to be used in stoichiometric way, and also osmium tetroxide. That is because the bidentate, these are bidentate ligands, they get bound to the osmium very strongly, and then they do not come out. So therefore such tightly bound complex although gave very high enantioselectivity, but then it was not catalytic. At the same time if we have a loose complex, that will also not give high enantiomeric purity, because if it is loose, that means it comes off, and therefore the reaction will definitely not give high enantiomeric purity, because it can also react with unbound osmium tetroxide. So we need to have a compromise. So a compromise has to be reached, and in this regard what was found by Sharpless, that synchronoalkaloids based ligands along with NMO gave the best results. So NMO was used for as a co-oxidant, but then synchronoalkaloids were used as chiral ligands. So these are the chiral ligands which are used in the asymmetric dihydroxylation. One of them is known as dihydroquinidine, the other one is known as dihydroquinine. They are pseudo enantiomers, they are called as pseudo enantiomers. They are not really enantiomers, as they are not really mirror images of each other, but they give different enantioselectivity, and therefore they are considered as pseudo enantiomers. Now, as you can see that the utility of such chiral ligands along with, as I mentioned, NMO gave the optical purity or enantiomeric purity being 6 to 88.3% and yields ranging from 62 to 90%. So, it seems to be pretty good, but then it is something that we need to worry about it, because why is it that the enantiomeric purity is as low as 6 and of course in some cases is as high as 83%. Now, if we look at one particular example, and if we can take this particular trans still bean, then we, under these conditions, this is the chiral ligand that was used, and 1.2 equivalents of the NMO was used and 0.2% of osmium tetroxide we used. It led to 89% yield of the product and 94% enantiomeric purity. So, if we start looking at various ligands and various kind of additives, and then we see that the yield is ranging from 8 to 95% and the enantiomeric purity is 20 to 88%, but then use of osmium tetroxide has decreased considerably, and therefore 0.2% of osmium tetroxide is needed for this particular kind of reaction. But then what is generally found that if we go from stoichiometric to catalytic process, it leads to decrease in enantiomeric purity. So, in general it was felt that the enantiomeric purity is still in these cases is not universally high in all the cases, but it also needs to be looked at it from catalytic to stoichiometric fashion if one wants to make it high enantiomerically pure product to be obtained. Now, why is it that when such a low enantiomeric purity is seen in cases where NMO is used as a co-oxidant? So, it was felt that this was due to the secondary catalytic cycle in which ligand was not involved. Now, when NMO is used as a reoxidant, it converts osmium 6 glycolate of this type to osmium 8 glycolate along with the expulsion of the chiral ligand. That means when this osmium 6 intermediate is reoxidized with NMO, it forms an osmium 8 glycolate, but then ligand comes off. Now, this osmium 8 glycolate, which is devoid of chiral ligand, then dihydroxylates some of the olefins, and that leads to low enantioselectivity. Because the osmium 8 glycolate is having osmium in oxidation state of 8, it can dihydroxylate some of the olefins, and that would of course be of low enantioselectivity because chiral ligand is not present. But then when Sharpless used potassium ferricyanide, potassium carbonate, tertiary butanol water system in place of NMO, the oxidant remains in water phase, and this allowed this glycolate, osmium 6 glycolate, to get hydrolyzed like this and release the chiral diol, which is of course of high enantioselectivity, and of course then releases the osmium 6, which then gets reoxidized because the oxidant is soluble in water phase, to osmium 8, which is osmium tetroxide. Now, this osmium tetroxide then interacts with the chiral ligand, and subsequently the osmium 8 modified with the chiral ligand then reacts with the olefin and forms this type of osmium 6 intermediate, and the reaction continues. Because of this, in general it was found that enantioselectivity or enantiomeric excess of the diol with potassium ferricyanide, potassium carbonate, tertiary butanol water system is much higher than just with NMO. What is the exact mechanism of this reaction? Initially what happens is that this osmium tetroxide gets attached to the chiral ligand, and the modified osmium species then reacts with the olefin to form this osmium 6 glycolate having the chiral ligand. Now this osmium 6 glycolate then gets oxidized with NMO, which is N-methyl morpholine oxide, and releases NMM, that is N-methyl morpholine. This osmium 8 glycolate upon hydrolysis releases the chiral diol and the osmium tetroxide. This entire cycle then of course continues, and this would be of high enantiomer selectivity because the chiral ligand is attached to the osmium tetroxide before it dihydroxylates the olefin. Now what happens is this particular osmium 8 glycolate, which has been formed by the oxidation of osmium 6 glycolate, oxidizes some other olefins present in the reaction medium and then makes this particular osmium 6 species. Now this oxidation of olefin by the osmium 8 glycolate is of low enantiomer selectivity because chiral ligand is not involved in this particular process. When this osmium 6 species gets hydrolyzed, it releases the diol, but this diol will be of low enantiomer purity. And so what needs to be done is, of course, this particular osmium 6 glycolate should get hydrolyzed to the chiral diol, which will be of high enantiomer purity, before it is oxidized to this osmium 8 species, because this is the osmium 8 species that is the culprit to oxidize the olefins present in the reaction medium, and there is a competition between this osmium species which has a ligand and this particular osmium 8 species which doesn't have a ligand for the dihydroxylation of the olefin. And because of this, the enantiomer selectivity of the chiral diol is low. So the modified reagent system of potassium ferricyanide introduced by Sharpless takes care of this particular problem and allows the hydrolysis of this osmium 6 species to the diol, and the oxidant is present in the reaction medium and is soluble in water that oxidizes the released osmium 6 species directly to osmium tetroxide. That means in the modified system, the hydrolysis is taking place first to release the diol, and subsequently in the same medium the osmium 6 gets oxidized to osmium 8, that is osmium tetroxide, and therefore this primary cycle is basically operating when potassium ferricyanide system is used, and that is the reason why potassium ferricyanide based system is of high enantiomer selectivity and gives the diol of high enantiomer purity. So basically the substantial developments were made. The change of oxidant from NMO to potassium ferricyanide in water and tertiary butanol medium, that led to the increase of the rate, and of course they also introduced some new dimeric ligands with the same two alkaloids but as a spacer unit, and a more convenient source of osmium tetroxide was used as this particular salt of the osmium tetroxide. So these are the structures of various spacers which have been used, and this is the structure where thylazine is used as a spacer, and this is DHQ and this is DHQD. This is another spacer here. Then you have this type of spacer is used which then allows two molecules to come in to the picture, and then we have this kind of pyrimidine system as spacer, and these type of spacers have been found to allow a sort of pocket of chiral nature that allows the epoxidation, dihydroxylation to occur to give high enantiometric purity. What is also found that if one takes the chiral ligand of any one of these type, say in this case thylazine is 5.52 grams, and then 0.52 gram is that osmium salt, and then potassium ferricyanide 700 grams and potassium carbonate is 294 gram. This particular combination of salts is known as AD mix alpha, and the other one in which this is different is known as AD mix beta. If we take a mixture of these, and this we use only say 1.4 gram of AD mix, any one of them alpha or beta, whichever one wants to use it, per millimole of the olefin in tertiary butanol and water medium, it is enough to give the dihydroxylation of high enantiometric purity. So, this has been introduced by Sharpless, and therefore it is commercially available with chemical companies such as Aldrich, and therefore one can simply buy these particular mixture of an oxidizing agent and simply put 1.4 gram of it per millimole of olefin and get the dihydroxylation. What is a mnemonic device that has been proposed by Sharpless based on a large study of various examples is that if the olefin is put it in this particular fashion where the small group and the large group and the medium and the hydrogen, it is a tri-substituted olefin. If we can orient it in this particular fashion such that the small group is closer to the northwest side, the large group is on the southwest side, and the northeast side is having this medium group, and the smallest group is towards the southeast side. If we orient it, then the epoxidation allows in such a fashion that you get the beta dihydroxylation, whereas in cases where AD mix alpha is used, then you get the dihydroxylation from the alpha side. So, the AD mix alpha and AD mix beta are basically designed based on such a mnemonic device, and therefore it is expected that if we put the olefin in this particular framework, in this particular orientation, then if we use AD mix beta, the dihydroxylation will occur from the top phase, and if we use AD mix alpha, then the dihydroxylation will take place from the lower phase. Now it is proposed that the reaction proceeds via this 4-membered osma oxetane via 2+2 cyclodation, whereas it is also proposed that it goes via a 3+2 cyclodation, and then of course eventually they come to this particular intermediate, and then the reduction leads to the formation of the diol. This particular 3+2 proposition was made by Corey on the basis of the fact that this 4-membered ring could be sterically bulky, whereas the 4-membered intermediate was proposed by Sharpless. So, there is a controversy, but then the results of course are the same, and one gets the diol no matter what happens, and we get the diol through this expected mnemonic device based dihydroxylation. Now the low rate of reaction of tri-substituted olefins, as we discussed, was due to slow hydrolysis of the osmium 6 glycolate, and this is what the osmium 6 glycolate is, and we saw that the hydrolysis of it is a must before it undergoes reoxidation. But the hydrolysis was found to be increased by about 50% if this methyl sulfonamide is used, and this allows the hydrolysis to be fast and therefore the enantiomeric purity is also affected by this, and it also allowed to do reactions at low temperature, and therefore high stereoselectivity is observed. Surprisingly, the terminal olefins react slowly in the presence of methyl sulfonamide, and this is something that is not very clear. Why is it so? However, it is very clear that the addition of methyl sulfonamide is something that allows the hydrolysis to be increased, and the molecules in which the trisubstituted olefins were slow to hydrolyze could definitely be improved, and high stereoselectivity is also observed. Now these are some examples of the osmium tetroxide based reactions. For example, we can take this epoxide having an olefin. Of course, this part of the molecule can also be prepared, in fact it has been prepared by using Sharpless epoxidation, and the dihydroxylation was carried out using this protocol which we discussed just now. And of course, if we take no ligand, we get both the molecules, and the ratio is 1:2. That means this cis diol and this particular diol, they are both formed in 1:2 if there is no ligand. If we use DHQ thylazine as this particular reagent system, then we get 10:1 ratio, and if we use DHQ DPHL, then of course we get 1:20 ratio of these two diols. So it is very clear that one can choose based on what one wants, and accordingly one can get the dihydroxylation. And one of these molecules was converted to castanospermine, which is a good glycosidase inhibitor, and therefore it comprises of a very important synthesis of such a molecule, which is useful in biologically. We can also make an anti-cancer molecule as camptothecin, where this particular olefin was dihydroxylated, and as you can see that the dihydroxylation leads to the formation. As we can see from here, this part has to be hydrolyzed of course to go to this particular amide, and the double bond was dihydroxylated, and as we can see from here that if we have dihydroxylation here taking place, then we can get this part. I am not writing it. So this is what we will get it, and then with this iodine calcium carbonate, this was oxidized to form the corresponding lactone, and this intermediate has been converted to the anti-cancer drug camptothecin. So one can easily see that how one can make use of such dihydroxylations in the synthesis of important molecules. So we will stop it at this stage, and we will take up the remaining aspects of asymmetric reactions, especially the reduction of molecules in such a way that they lead to optically pure reduced products. So till then, bye and thank you. We will see you next time.